Yeah, so we said in this video we are going to just look at the mathematical optimization, just the high levels. I'm not going to get into the deep calculations. We're just going to do a bit of the high levels of the mathematical optimization of the Lasso and the ridge regression. It can be shown that those equations that we're writing, it can be shown that the ones that we're writing, right? For the Lasso, we're writing that it is RSS plus what? Lambda j equal to 1 to p and bj, right? It can be shown that okay, let me just write for the ridge as well. Ridge, which is RSS plus, remember at the back of your head what RSS can be rewritten as, like the original form of RSS. That RSS is equal to the summation of I for all observations yi. So this is going to be y, what did I write here? Yi minus beta naught minus summation of j equal to 1 up to p beta j xij squared. Remember this. I think you remember this, right? So using optimization, it is solving these problems here. When you say minimize this, that's what we write. That's what we're saying. Minimize this quantity. That's what we've been saying. It can be shown that using mathematical optimization, it is the same as solving these problems. Minimize the beta of this function. Equal to 1 up to n of yi minus beta naught minus summation of j equal to 1 up to p of beta j xij squared, right? Minimize the RSS. We are minimizing the RSS subject to j equal to 1 to p less than or equal to s. This is the Lasso problem, and the ridge problem will be minimize beta for this part here, which is the minimize the RSS. That's what we're saying. Minimize the RSS, right? Minimize the RSS subject to j equal to 1 b beta j squared less than or equal to s. That's pretty much mathematical optimization. That's the mathematical optimization. That's the mathematical optimization part, right? We can use, and it can be shown. You can go from here to there using Lagrangian. I think they are called Lagrangian multipliers or functions. I'm not quite sure. I've forgotten this part, but I think it's Lagrangian multipliers or functions, where you change this optimization problem. Now you have your function. You have your function with beta naught, beta 1, and with your betas and stuff like that, plus the lambda, and then you create a new function. I'm forgetting what exactly it is called, but it is not part of this course exactly. When I'm recording my mathematical optimization course, I'm sure I'm going to include those. We are going to discuss those, right? We're going to discuss those. What that means is for every value of lambda, so for every for every value of lambda, there is an associated S, because that's what you now be changing. You now be changing this. You now be changing this using this lambda, and you have your S. Your S will even be involved in the new functions and stuff like that. So it's going to be, so for every value of lambda, there is an associated S. So these which means if we solve using the S, we'll just get the same Lasso coefficient estimates as if we have done this, as if we have done the original, using the lambda, but now we're using the S, right? Cool. So so now let's just imagine we have two predictors. It's always easy to start off with less dimensions, right? When p is equal to 2, when p is equal to 2, right? What you can see now is these equations on the right hand side. What are they saying? Let's rewrite them here. So this one here that is saying, let me put the summation sign even. J equal to 1 p. You see this one here subject to this. This is the constraint, right? This is the constraint. We need to minimize this subject to. Let's look at the constraint. So the constraint is going to be bj is less than or equal to s. So that is our p is equal to 2, right? So it means summation of j equal to 1 up to 2 of this bj, which means modulus of b1 plus modulus of b2 should be less than or equal to s. That's what it basically means, right? That's for the Lasso. For the regression, let's look at this. 2 beta j squared less than or equal to, that is beta 1 squared plus beta 2 squared less than or equal to s, right? So what this basically means, what type of shape is this? This is a diamond shape. If you put it on a Cartesian plane, it becomes a diamond shape like this. And we are saying this is our constraint. We want to minimize RSS such that it is constrained by this diamond. And looking at the sign, it says less than or equal to s. So which means the length here will be s, the length here is an s, the length there is s, the length there is s. So we want to be inside here. Why am I saying inside? Because it's saying less than or equal to s. And when it says less than or equal to, it means including the boundary. Including the boundary here. So we are going to minimize, this is the constraints, the constraining set. This is the set that we are interested in. Looking at this second one here, it is a circle centered at 0 with a radius of s, right? And the same thing, less than or equal to means the boundary is included and the inside as well. So this is where we are. So we are going to, what we are basically saying for Lasso is minimize RSS, that RSS function, subject to the values that are inside there and on the boundary. That is for Lasso. If your function is here, we're like, nah dude, it is not fitting our boundary. It's not in our boundary or our constraining boundary. It's not there. This is the boundary we're talking about. We want to find the minimum RSS as long as the beta naught, because this is going to be beta naught and this is going to be beta 1. As long as beta naught and beta 1 are both inside there, wherever they are. So for each one of these, we want to find the minimum RSS for each combination of these. That's it. That's the right way to say it. For each combination of beta 1 and beta 1 inside this boundary or on the border, wherever, each of these combinations, we're going to try find them which combination gives us the minimum RSS. That's pretty much what we're saying. Same as for this circle here. We're saying minimize the RSS with ridge regression, minimize the RSS subject to a circle centered at 0 with radius s. So is this the combination of beta 0 and beta 1 that gives us the minimum RSS? We have to test that. Or is it this one? This one? Is it this one? Or is it this one at the border here? Is it this one at the border? Or this? Or that? Or that? Or that? You know what I mean? So we have our function, and we are going to say when you bring your function inside this border, when we bring our function inside this border, where is it going to get there? Inside or on this border, where is it going to get the minimum? You are going to see that it's quite an easy concept, that part. So now what people usually call as sometimes people call as the budget, because that's what we are working with. We are working with this as the budget, right? It's called the budget because if imagine, let's now imagine. Let me see if I can write a scenario here. Okay, yeah, but no, don't. Okay, I can explain it now. So since we have drawn these circles, right? These are combinations of beta 1 and beta 2 that satisfy the budget, right? If let's say our combination for least squares, our least squares combination was here. That is our least squares budget. Our least squares beta 1 and beta 0 were beta 0 and beta 1 according to least squares, right? According to least squares, that's where they were. According to this budget, the diamond that we have drawn, they are outside the budget. So which means according to this, they are failing to satisfy our budget. So it means they are actually way better beta 0 and beta 1 that we can look for. We can actually look for way better ones that will fit our budget. So it means maybe let's look at the function as it approaches this boundary, because when it approaches this boundary, our lasso is now starting to work. Our bias is being introduced, but it's going to be introduced. We are moving away from least squares, but we are going to get better beta 0 and beta 1 is when we get to this budget, when we get to where the budget is. Same case with this circle. If they're still there, let's just imagine they're still there and you forget about the diamond. They're here where they are. They're outside the least squares beta 0 and beta 1. They're outside this budget that we have. So it means they are better, although we might be introducing a bit of error, but in the long run, it's actually better for us to choose other beta 0s that are in this budget, than to use the least squares one. That's what ridge regression does. It just shows you that where is your beta 1 and beta 0? They're outside my budget. Okay, cool. If they're outside my budget, then let me choose other beta 0s that are inside the budget. What this also means is if the budget is large, let's say my circle was this large. Let's say that was my circle, right? If that was my circle, can you see it now includes my least squares beta 0 and beta 1. So there's no point in looking for any other beta 0 and beta 1 because my least squares will be the most efficient or the lowest beta 0 and beta 1 for that situation. If my beta 0 and beta 1 are inside my budget, then there's no point. There's actually no point in looking for other beta 0s and beta 1. We might as well use my least squares beta 0 and beta 1. I have reached the optimal solution. We would have reached the optimal solution. So, okay. In that case, usually in that case, it happens when, let's say, for example, your lambda is equal to 0. If your lambda is equal to 0, you do not have any constraining budget. You are not doing any lasso. You are not doing any read linear. You are not doing any read regression. We might as well say our S is equal to infinity in that case. We might as well say that because we are not even doing any lasso or any ridge regression. We are not even doing them. So that's why we just go for the least squares beta naught and beta 1 when our lambda is 0. When our lambda is 0, we are not even doing Lasso and regression. The beta naught are inside our budget. So that's what it means. So that's what it basically means. So we want to choose an S such that we actually gain something from doing these shrinkage methods, right? So now what we can now do is now that we know the boundaries and the budgets, right? Why is it that the Lasso sometimes puts things equal to 0 and the ridge regression pretty much rarely does that? So this is the situation that is happening. Our Lasso boundary is like this, right? That is our Lasso boundary, like this. And our ridge regression boundary is like this. Okay, that's a bit skewed. Let me try. Okay, so our ridge regression boundary is like this. That's a bit better, right? So that's our budget. Cool. So now let's draw our function. Let's draw. This is where our least squares beta naughts and beta 1s are, and we agreed they're outside the budget, so which means there are actually beta 1s out there in the world in our boundary. Let's look for them. So what we are going to do is we are going to do something called level sets. We are going to draw level sets. So a level set is a contour or a line or an ellipse. We can call it an ellipse. An ellipse that has that connects values with this, that connects values with the same RSS value. So if I'm to draw a contour like this, I'm not just going to draw a contour. I'm going to look at my RSS values. When you calculate your RSS value, it will say RSS of 9.9, and I'm going to look at all beta naughts that give me that RSS of 9.9. So which means here, this contour we have the same the combination of these beta naughts and beta 1, they have the same RSS value. Also these beta naughts and beta 1, because this is beta naught, right? I hope you agree that we are drawing this on the same axis with beta naught and beta 1. So these ones, they are blue, they are just the optimal ones when it comes to least squares. But this beta naught, right? This beta naught, it has an RSS value. I'll be like, oh yeah, you beta naught and beta 1, this combination at this corner here, you have an RSS value. They'll say yes, our RSS value is 0.8. And I'll look for all beta naughts that have an RSS value of 0.8, and I'll connect them with a line like this, and it becomes a contour like that. So it becomes a level set like that. So if I keep creating those level sets, you see I'm creeping towards my boundary. Can you see that? I'm creeping towards my boundary. Level sets, they never cross because they are connecting different values of RSS, so they never cross like I did here. It's a mistake. They never cross like that. Cool. So you see what is happening here. According to least squares, it has this RSS value. Right? And then we drew what do you call this? We drew other contours of ellipses that share a common value of RSS. This contour line, this contour here, it is a certain value of RSS. This one, a certain value of RSS, certain value of RSS, certain value of RSS, certain value of RSS. Now, as the contours expand out away from this point, from this least squares point, right, the RSS increases because we are introducing a bit of bias. Remember, when you move away from the RSS, we are now introducing a bit of error at the end there, but there's something that we want to gain. So as we move away from this point of least squares, we are actually increasing our RSS. We're increasing our RSS, right? So what we then see when we're doing the lasso, we said, although we are increasing our RSS, our error, we want the beta naught and the beta 2 that will minimize whatever function we have, but subject to our budget. This does not fit our budget. This contour line does not fit our budget. This contour line does not fit our budget. This contour line does not fit our budget. It's still outside our boundary. This one fits our budget because it just touches our contour line here. Just touches our contour line there. And we said we want to look for the beta naught and beta 1 where this function just touches or goes inside our budget. Like enough, it just touches there, and then when it just touches, it satisfies this less than or equal to. It satisfies the equal to sign, the equal to part, I mean. And then when it just touches, this is where the magic happens. Those are the beta naughts that we want. Those are the beta naughts beta naught and beta 1 that we want. Yeah. Where it just touches our budget. So although we've increased our RSS, we have found beta naught and beta 1 that are less than the least squares beta naught and beta 1 that satisfy our budget. Straightforward like that. Same happens for this. Same happens for when we're doing ridge regression. As soon as it just touches the circle, we have our special new beta naught and beta 1. Right? We have our new beta naught and beta 1 that is satisfied the ridge regression minimization problem. We have increased RSS. I keep emphasizing that we have increased RSS. Yeah, sure, but in the long run, it's going to be beneficial because we have way lower beta 1 and beta naught satisfying our budget. That are satisfying our budget, right? So now the difference between lasso and what do you call this? And ridge regression is because lasso has these corners here. It has well-defined corners, can you see? And ours is a smooth circle for ridge regression. It's like a smooth circle. The chances are high that the contours, these contours of RSS, they are going to hit the lasso boundary at a corner that is shared by an axis like this. Can you see? It's being shared by an axis. Let's write out the betas there. Beta 1 value is some value, right? It is some value, cool. But what about beta naught value? Can you see that beta naught is turned to 0? So now we have 0 and beta 1 and some beta 1 value. In this case, we still have beta naught and we have beta 1. So this is why sometimes the lasso will make some coefficients disappear. Yeah, I just used beta naught, although in the real lasso, and we are using real beta naught like the way we are using before. Beta naught here is just arbitrary. It's just showing you that some coordinates. Imagine this was the edge coordinate and this was the weight coordinate. Edge would have the coefficient for edge would have disappeared. It would have disappeared because the minimum beta naught and beta 1 that are happening in our budget are at an axis, at a corner with an axis, and then so this beta node disappeared. It is very rare for that to happen with our ridge regression that has a secular budget. A secular budget, it will be very, very rare. It will be very, very rare for it to make some betas disappear. It actually will not make some betas disappear. It will not make some betas disappear. In 3D, this becomes like a, I don't know what they call it. There's a special special name for a diamond in 3D, right? We can just call it like a diamond. And then this in 3D, it becomes a sphere, right? It becomes a sphere when our P is now equal to 3. Our P equal to 3. This becomes 3-dimensional. Everything becomes 3-dimensional. This becomes a sphere and stuff like that. So as you increase your P, you can complicate the shapes as much as you want, but this is the basics of mathematical optimization of what is really going on here. It is just rewritten what we had initially, what we were dealing with initially. Just rewrote what we were dealing with initially, right? What we're dealing with initially in mathematical optimization format, and then this subject 2 created a budget for us that we needed to work with. We're like, let's minimize the RSS, but when we minimize the RSS, we want to get, in other words, we want to get the minimum RSS subject to our budget. So when we say the minimum RSS, we basically mean the first contour line that just touches our budget. If it just touches our budget, that's the minimum RSS that we're going to take. That's the same thing. That's exactly what we did here. We're patient, increasing our RSS. RSS is laughing, saying, yeah, it's increasing. But now we knew as soon as we create a contour line that minimizes our budget, that's point when it just touches our boundary, those are the betas that we are looking for. And we saw that for Lasso, the budget becomes a diamond. For Lasso, the budget becomes a diamond, and when P equal to 2, and for ridge regression, the budget is a circle. P equal to 3, the circle turns into a sphere, turns into a spherical object. P equal to 4, some complicated shape, and stuff like that. They keep complicating like that, but the principle is the same. We increase our RSS. As we're increasing our RSS, the very first contour line of RSS that just touches our boundary, or satisfies our budget, is the one that we want. If we didn't have an equal sign, because we had an equal sign, right? So it was perfect that it just touches the boundary. But if there was no equal sign, we would need to move just a little bit inside the circle, just a little bit into the circle. Then we have satisfied our budget. So that's basically what it is. So I hope this mathematical optimization explanation sort of gives you something to look forward to when I record the full course on mathematical optimization. But it's quite fascinating to see some of these things come to life, right? It's quite fascinating. I think for the shrinkage methods, I am pretty sure that we've exhausted the shrinkage methods. I'm just looking at my notes right now. Yes, I think we've exhausted what we wanted to talk about. Of course, selecting the lambda is done through cross validation. It's done through cross validation, the same way we discussed it last time. Same way we discussed it when we did best subset selection methods and all of those ones that we're doing, right? In the next part of the course, we're going to move on to, or next part of this chapter, we're going to move to dimension reduction methods. That's where we are going to get into things like principal component analysis and all of that good stuff. So stay tuned for the next upcoming videos.